Greetings, welcome. In the last video I was talking some theory, so in this video we'll get back to the fun part, which is experimentation, and there are 3 experiments that I want to get done. However, even before we do that, I want to offer a correction to my thinking that I put out in the last video, and I think part of that was coming back from travel and being on 2 to 4 hours sleep the night before, and part of it was just sort of in the back of your mind. You think that can't be, the wire gauge isn't going to have an effect and whatnot. So what I was saying was that if you have the diameter of a wire, then you will have 1/4 of the amps flowing through the wire. Because, again, you can think about it as a square wire. If you have the diameter, the surface area of the square will be 1/4 of what it was before. And that's correct. So let's just stop there for a minute and review one more time. The unit of magnetomotive force is the ampere turn, defined as how many amps you have flowing through how many turns. So I was saying, if you have the diameter of the wire, your amps go down to 1/4 what they were before, and since the wire is now half as wide, you can fit twice as many wines. That's actually only true in the case of a single layer coil. If you have a multi-layer coil, you're just taking that square and dividing it up into 4 pieces. So with the multi-layer coil, if you have the diameter of the wire, your amp flow will be 1/4 what it was before, but you will not have 2 times as many wines, you will have 4 times as many wines. So the ampere turn is defined as amps through turns. 1/4 the amps, 4 times the number of wines, the exact same ampere turns. However, you're now drawing 1/4 of the amps. Voltages remain constant. And the ampere turn is the unit of magnetomotive force. So again, it's sort of, I'm still kind of recoiling from that, but that follows from the definitions. So that's certainly an experiment that needs to be done. We're not even going to start with that. We're going to start by looking at placement here and here for the coil. And let me just describe the setup real quickly for people. We have this rotor, and the magnets are going north-south, north-south. And this flips on at the appropriate time and the appropriate orientation to push the rotor around. This is your drive coil. Here you have the generator or pickup coil, as I like to call it. Pickup like the humbucker pickups on a guitar, doing the same thing before they get amplified. In this case, the change in the magnetic flux isn't from a guitar wire, it's from these magnets spinning past, and it goes out to a capacitor here. You can put that on a meter and then put, say, a 1 kilo ohm resistor across it and see, okay, what kind of power are we getting out from here? Likewise, when this coil, the drive coil, has its magnetic field changing, that can be captured through a bridge rectifier. I put that out to another capacitor, put a resistor across there, and you can say, okay, what kind of power are we getting back from this flyback spike, or whatever the heck you want to call it? So that's the setup, is to look at both of those. And the conundrum I was having, well, before I can even describe the conundrum, I have to show you a trend that has been invariant with all these experiments I've done with this particular sort of setup. That is, so here you're at 2 volts and we're drawing 8.2 milliamps and we got that many milliwatts. That was the RPMs we're seeing. We were seeing 3 volts out of the spike across the resistor here. And okay, we're getting almost 6% back from the flyback. Then you go up to 4 volts and it's 16 and then 24. And I've gotten out to nearly 69, nearly 70% now. And so I think I can probably get out to 70% with this setup if I, really spend some time with it. And I don't know why that happens. I have some thoughts, but I'm not sure. I will say if you're just pulsing this coil on the desktop, you don't see that behavior. So I'm not entirely sure why that happens. Now the next thing is that I noticed if you bring the coil in and or you make the air gap more narrow, there is a point where, okay, I brought the coil in and my amp draw is like half what it was before, and even when this is under load across a resistor, the rotor is spinning at the same speed or faster. However, the spike that you're getting back across here has gotten worse. So in other words, you're getting more out from here, you're getting less out from there, and overall you're making no progress or going in the wrong direction. And that's what I was thinking for a while, until I realized I was like controlling for or looking at it in terms of voltage. So, 2 volts, 4 volts, 6 volts, whatever. I would say what you're really sort of interested in for this game, though, is what are your milliwatts in versus your milliwatts out. Milliwatts out here, milliwatts out there. So in other words, we see, just this improvement with voltage, but maybe it's more of a function of how many milliamps, again going back to amp turns, that you're throwing into the coil. And I wish I had a clear understanding of this trend, but it's obvious, you could be bringing this thing in and you're still at 12 volts, but you've gone from 12.3 milliamps back to 8.2, and it's like, oh, why did the spike stink? Well, the spike stunk there too, and voltage is arbitrary. You could just turn it back up to where you're getting 12.3 milliamps out, and now if instead of getting 7% back from here, you're getting 12% back from there, then that is an improvement. So again, I want to look not so much focused on the voltage as the milliwatts out here and here and the milliwatts in. And so that's, I'll just sort of illustrate for you what I'm talking about, and then we'll look and see. And there's going to be the spot where the torque will be highest, and maybe you need to throw in some more of these to bring this here. But in general, when this thing is lined up right under the magnet is where you'll expect the most torque. But the amp draw goes down because these magnets are interacting with the coil and preventing current from feeding in. But if the spike, what you're getting out, is a function of your amps in, then I'm all right with that. We got plenty of room to run here. These are 100-volt AC relays, and I was stopping at, where are we? Stopping at like 36 volts there, because you're running fast enough. The thing you're worried, is this thing going to fly apart? Or are you going to start putting so much power through that you're frying the thing? But we run up to 50 volts, so let's do that first, and that'll be a fun experiment. The second one is wire gauge, the third one is the second coil. I guess before we even spin it, one thing I like to do, just throw 1.8 volts in there, and oh, it's good I did that. Something's wrong. Yeah, one of the relays down there wasn't setting right. Now I'm only checking 2 of them. I mean, technically I should check the other 2, but I'm going to trust that we got it. And let's just pick an arbitrary value. Let's run it at 6 volts. The contraption is spinning. So this is good. We're at 6 volts. And this experiment will have 3 parts to it. The first 2 parts will be to show you, what I was seeing and a bit why I was confused. And the third part will be, again, to kind of put it in terminology that I'd be more familiar with, to normalize upon milliwatts in versus milliwatts out, and here and here, not on voltage. So what are we doing? We are spinning at 949. These things take forever to settle down. That's one of the problems with them. 949 RPMs. I just cut and pasted a couple other examples at 6 volts. I suspect these might have been with the 6-magnet rotor. I don't know. We're drawing considerably more milliamps there, like at 22. So much of that depends on where the coil is. But there, we were at like 660 and 768, and I think I just said we're at like 960 with 22 milliamps. Let's just jot this down, we'll figure out first where we are. Here I was getting 24% back, 29% back. Figure out where we are on that front. So we are at 6 volts, 22.8. That's what I'm going to call it. Yep, that's what I'm calling it. 22.9. And so this will be important going forward. We're drawing 137.4 milliwatts. The RPMs, I can't remember what I said, 960 something. 950.3. Now, this is just freewheeling right now, with the exception of any minor cogging. The air gap there is quite dramatic between the pickup coil and the rotor. So we're just freewheeling, doing 950. The spike is not 15.4. The spike is now 18.8. So kind of in the ballpark of what we were seeing before. Again, I don't remember the rotor. It might have been the same rotor, just different positioning of the drive coil. 25 rounded 26 versus closer to 30 and 24. So that was fun. And now what we want to do is connect, if we, half the battery be dead. Just freewheeling, we're seeing 8.92 volts across there. What I want to do now is connect the 1K ohm resistor across this. So now what's going to happen is there's going to be drag on here. This is going to slow down. As it slows down, the amp draw will increase. The spike will go up ever so modestly, maybe a bit more than that, but it will not compensate for the increased amp draw that we're going to get from the slower rotation. And eventually this will settle down to a value which will allow us to figure out how much we're also getting out from here. After letting our rotor settle down to what it wants to spin at under this load, we see that we're spinning at 700 and we'll call it 767 RPMs. Now the duty cycle, of course, hasn't changed at all, but it's the nature of reactive resistance. As you bring the coil closer to saturation, there's less resistance, and so we're drawing considerably more milliamps. What do we want to call that one? I'm going to call it 29.8. 22.7, yes. So we're up from that many milliwatts to that many milliwatts input. Our spike is at 18.8 there. What is it at now? Our spike is now at 22 point, let's call it 22.2. So oddly enough, in this particular setup, and it generally goes the other way. It generally goes as you're loading it, it's worse. You know, it's such a Rubik's Cube. Generally, it doesn't do this. But we're now getting 27.7% back under load. And then here's the icing on the cake, is that we're under load. And we're getting 3.82 volts here. So if we put in that we're getting 3.82 volts there, we see we're getting another 8% there. So our total is 27% back from the back spike, 8% there, for a grand total of 35.8% efficiency, which is actually kind of nice. That's 33.2, and this one was also 33.2, even though they were different. This one's a little bit better. So you could fiddle around a long time with that. Now, here's what I want to show you that was sort of a conundrum, which hopefully I can kind of understand a bit better now. I put so many markings there, you know, just looking at things. What I'm going to do is put down a piece of tape there, and what we're going to do is, keeping it on that line, we're going to slide this in so that it's no longer, I mean, look at how stinking far off center that is. I mean, that's not where your highest torque is. Okay, so I'm going to disconnect the load, and we're going to scooch this guy into where he's close to right under the magnet. And I think that's, he's kind of sideways though. I think that's not bad there. And I'll show you again the conundrum I was up against, and then what we're going to do is, to heck worrying about voltage, we're going to look at milliwatts in, milliwatts out, and I'll show you how we're going to do that. But first we need to gather this data point, show you, the issue that I'm talking about. So I've moved the coil in at the same, around the same position. I don't know if the core is exactly lined up under the magnet, but it is sure a heck of a lot closer than when we had it out like that. So the most dramatic thing I think you can see is that the amp draw is now, we'll call it 10.8, whereas previously when it was freewheeling, the amp draw was 22.9. I've just copied and pasted that a second time as we put in the new numbers. So the amp draw has more than halved. What is our rotational speed while freewheeling? Our rotational speed freewheeling, I think you got to round it to 855 versus 950 when we had so much more than double amp draw. All right, well, this is actually astonishingly bad. So if we look at what we're getting out for our spike, it's going 5.5. I'll be generous and call it 5.6. So focus. We put 5.6 in with the spike. Despite this having gone down by half, we're getting a whopping 4.8% back instead of 25.7% back when I moved that in. Hence why previously I was like moving it out, and like, you dirty rat, you farting bastard, I'll get you yet. But what we will also see, now we're going to load it is that this part will increase, but it won't be enough, I think, to get us anywhere close to where we were before. And that is the conundrum I was speaking of, that I think, we can, hopefully we'll see that solved here in the third part of the experiment. So I connected the resistance. This is like, it takes so long to settle down. It's like the ends. It takes a long time to say anything in old English. And we don't say anything unless it takes a long time to say. So I think it's about settled down to where it wants to run. And here's something I want to show you, is that it's spinning at, we'll call it 768 RPMs. Now if we go back to what we just did before we moved the coil in, we were spinning at 767, 1 RPM slower. We were drawing 29.7 milliamps. Now there's more torque. We're spinning at 768, but we're drawing, what do we want to call that? I'm going to call that 14.6. 14.6. So under load we're spinning a teeny bit faster, and we're drawing a little bit less. Yeah, just a little bit less than half the amperage. So that's all good. This is all bad. Let's check out the spike here and then add in the rest, and you can see why I was, curse you, John Badini. I'm kidding, he's dead. Bless him. Love the man. 7.4. So we put the spike in, and once again, oddly enough, I mean, generally it moves the other way, but this time we did a tiny bit better, 5 to 6% back. But this is the other part. What is this thing sitting at? It's going to be, since the same RPMs, right around 3.82. I don't know why it's saying 3.77 when we're spinning an RPM faster, but I will accept that. Maybe I bumped that or the wind moved it. So 3.77. And we see we've jumped up to 16% back from here, but we're at 6.3% instead of 27% back there. The total efficiency of the system has gone way down. And here it's not exactly the same, but here we're drawing 93 milliwatts, 24, 16, and we're down to 6. Or over here, where is it? 104 milliwatts, 29, 14 milliwatts, 9. So there's that trend, and what needs to be done now, I mean, the voltage is just sort of an arbitrary thing. We need to increase the voltage here, the voltage environment, because what you're really interested in is milliwatts in, milliwatts out. Increase the voltage here till the milliwatts here are about equal to here. Now, as I said, these things take a long time to settle down, so I don't think I'll get it exactly right, but we'll get it within a couple or a few percent, and then re-examine the spike under load. And I'm hoping, haven't done this yet, I'm hoping when we control for milliwatts in, that the spike will be looking closer to that, and we'll still get this nice benefit. So undo the load, crank her up. I have no idea what it should be at, but I'm guessing around 9. So I've spun the contraption at 9.2 volts now, and we are at, I'm calling it 14.7. So if we say 9.2 volts, 14.7 milliamps, our milliwatts are 135.2, they were 137.4 there. What is Where are we? What is our rotations? It's not 855. It is 1206. 1205, 1206. Let's put that in. What is our spike? Our spike is 10. That's easy. So 10. And the back spike still stinks. 7.4 is better than 4.8, but worse than 25.7. But as Bob Ross said, there are no mistakes, just happy little accidents. So I'm already formulating an idea here that if we control on milliamps, then if we bring the milliamps up to 22.9, we're going to see that same number. But before we do that, we need to complete this part, which is, if we load it, what are we going to see for the sum total? So under load, this thing has settled down to 1060, where are we? 1061, 1062. Our amp draw went from 14.7 to about 20.3. Our spike, be generous and call, well, 14.6. So that part improved a bit, but still nowhere near there. And our 5.67. 5.67. Okay, so it's a good bit better than before. We're still not back to where we were when this thing was crazy out there. If you can possibly bear with me without pulling your hair out, for a bonus part, instead of normalizing on milliwatts, let's normalize on Andre ampere current flow. So 22.9, we only made it back to 14.7 instead of 22.9. If we get the amp flow to 22.9 and this thing doesn't fly apart, because we were doing 1200 RPMs before, we're going to be going fast. Alright, I cranked it up to 16 volts, and the engine's got to take much more of this, Captain. The buckling. Actually, it's fine. There's a little bit of vibration. Yeah, we're going at 1760 RPMs. Maybe still climbing a little bit. And we're drawing 23, 20, 22, 20, 23.9 is what we're shooting for, and I think we're right around there. That's where we were before freewheeling at 6 volts with the thing out there. So now to get that same amp draw, we have to go up to 16 volts. Let's start to put in the numbers. So 22.9, our milliwatt draw is like nearly tripled. Our spike's gone up a little bit, 23 point something, 20, let's figure that out, 23.5. Well, the spike still kind of stinks. Let's load it. And slow it down a little bit and see where we are with the two of them combined. Okay, last part, and we'll wrap it up. And this is it under load. We're now drawing 30.8. RPMs dropped to there. Spike went from there to there, so this went from there to there. We're getting that much back from the pickup for a total of that, 37.8, which is now at last better than 35.8. However, if we go back to, what are we saying there, 37.8. If we go back to here, I don't have a 16 volt one, but you know, at 18 volts we're at 55, so probably about like at 50. So hope I didn't bore people to tears, but it's my party and I'll cry if I want to. We did actually learn a couple things, not to cry too much. If you'll bear with me for a brief debrief. There's one thing that I thought was interesting, and that actually makes sense, I think. So here we were at 22.9 milliamps, and the spike was 18.8. Here we were at 22.9 milliamps. The spike was 23.5. So the spike, in terms of the milliamps, the current, was better here. The RPMs were 1700 versus 950. And so I believe the improvement in the spike in terms of milliamps was that you're going faster, you're getting a briefer pulse, and you're getting a higher Q factor. That said, the take home from this that I get is, goofy as it seems, you want the coil out there, because here we were drawing 137.4 milliwatts, and you know, our total back was 35.8 at 6 volts, 25, then 27 loaded, and then 8 from there. Now we got it out to 16, 17, around there by increasing the torque in here, but it screwed with the spike. And so by, you know, getting this normalized to the milliamps, you're at 16 volts, and so your milliwatts are 366 versus 137 in order to start to improve. So I think this offset way is better. That's the take-home message there. Now the problem that you have is the little torque that you have from a pulse motor is now even less in the position where you're getting the best spike back. So, you know, we were getting a whopping 16-17% back here, and you're down to like an 8%. But that seems to be the best place to run it in. So that's experiment 1. And then experiments 2 and 3, it seems at first glance that there are ways to arbitrarily improve magnetomotive force. So it doesn't matter if you're starting at 8% or 16%. And the two ways, the one way I was, you know, very confident of, and still am, is by adding a second coil. So in other words, you just need wire in the proper magnetic environment. The second way, which I had dismissed until I thought about it a second time, is wire gauge, and I can't figure out how that wouldn't work. But you know, famous last words or something like that. But that'll be the second experiment, will be wire gauge. And then as I'm doing that, so in other words, go to this is 24 gauge, go to 26 gauge. Again, look at the spike, again, look at this, what you're getting back from there. And what you're getting back from here should improve, and I suspect the spike should do just fine as a function of milliwatts in, milliwatts out. Depending on the results of that, I'll wind another 24, another 26 gauge, and go from there. So again, sorry for if it was a very lengthy video, but I'm having a ball with this, and I hope people get some modest enjoyment out of it, or more than that as well. May you stay healthy, and remember to keep smiling. Take care, everyone. Bye-bye.